discount right now. So with our 30, we're hoping that it's a lot more affordable for a lot of you folks. Don't forget our hotel rates are like $130 a night. You can now register for the hotel. Just call the Crown Plaza up. Make sure you use the code TTC, Tango Tango Charlie, and they'll get you set up right away. I guess the main thing I would be looking at would be we just have a great set of speakers. I mean, even after we had our conference schedule kind of finalized, we were able to squeeze a few more speakers in there, and I dare say that all of you will have a great time. I guarantee it. If you don't have a good time, come and see me, and we'll make it right. Anyway, and last but not least is our YouTube channel. We need people to get signed up for the YouTube channel. The YouTube channel is our bread and butter, and we're up to 1,500 videotapes. In about a couple more weeks, we have a gentleman coming in here to help us convert approximately 100, 200 VHS tapes to videos from the Tesla Society conferences, and we'll be putting those up there as well. I say, if you get a chance, go up there, check it out. We have a lot of free videos up there for you, and all these Sunday sessions are up there. Too. Just go to Steve's place on teslatech.info and click on it, and it brings them all up. Instead, I'd like to introduce Ryan here, and right now I'm having some difficulties. I ask you please bear with me. I have an underpowered computer here, and let's see what we got here. Okay. I don't understand what's going on here. Anyway, let me introduce Ryan here. For some reason, my screen is all messed up, and I can't see what I'm doing, so I'm doing this in the dark. And I'm just going to back out of here. And Ryan, you just got to introduce yourself, okay?
All right. Yeah, Ryan Thompson here. Most of you may or may not know of me. For the ones that don't, I've been a longtime lover of John's work. But as I've gotten older and I've kind of got involved and studied his work, I realized there's a lot of things that are, I guess, mystique or mysterious or problematic, or people may not know. So I'm kind of hoping that the presentation here tonight will kind of explain or maybe help some of that information. Big shout out to Steve and Tesla Tech for giving me the option to be here tonight and kind of guiding me to what I got to do to his program. I will be a speaker at his Tesla Tech convention coming up here. Been pretty excited to go to one. Most time work kept me away. So this time I said, hey, Steve, I got some stuff. Let's sit down and talk. And kind of that's what brings me here tonight. So without getting too crazy, I'm just going to kind of jump into it because I'm just kind of that way. At the end or towards the end, if you guys have any questions, if we can interact, which I think we can through the chat, feel free. I'm going to kind of just narrate through my slides, and I got some videos that you guys might find enlightening. And most of this is just kind of everyday stuff I'm just going over, but I know the audience doesn't always know what's going on. So this kind of gives me a way to kind of lay the groundwork. The convention will have some of this stuff and a lot more hands-on, and I think that will make it kind considerably easier for the new audience. The guys that are really smarty, I'm going to probably bore you tonight because I'm just going to be with the basic overview of the basic ideas as my beliefs, the way I see them. So I'm not trying to really prove or disprove anything. So just keep that in mind. This is more of a hands-on show and tell overview. It's not to get into the nuts and bolts of things like, flux density and direction of flux and things of that magnitude. It's going to be much more of an overview. So, right. So I'm going to click on this first slide. Hopefully it'll pop me up. Okay, there we go. Right. So if you want to reach out to me, this is how to get a hold of me. If anybody is on my YouTube page, socialmediainfo.us, if the live stream is working, great. I don't think it is, but it's kind of like anything. We just learn as we go. The phone number down there is manned by me. That is actually a physical phone. It's not a virtual phone. So you will probably get dumped with a voicemail just because, like everybody else, I work and times are hard. So I work all the time. The Gmail is self-explanatory. The kits and info is kind of a neat thing. The actual motor generator system, Bendini system, recovery board, all that. You can go out there and inquire about purchasing. I will also have some stuff at Steve's convention, Tesla Tech. I won't be selling anything there because I don't have anything yet of any quantity, but I just figured I'd let you guys know. But there's my contact information. So at this point, I'm just going to keep driving the slides here and basically narrate to you guys. So I apologize if this is boring for some people, but I know a lot of people don't know some of this stuff, and these analogies I find are helpful. And that's what people in the past have told me. So like I said, hopefully it's entertaining. Hopefully you guys learn something. Hopefully you get something out of it. All right. So what I'm basically going to go through here is the E-field through observation, no math addition. And that's because I'm not going to talk formulas, but I'm going to talk terms and what these terms mean. Well, I got a screen here I want to get out of my way, but I'll make it work. Okay, so E-field through observations, no math addition. Potential. Why will a neon light bulb light up if I touch one end to myself and insert the other end into a wall outlet? Note, we are taught that this is dangerous. And it is. If you're amateur, don't do this. I will provide a video. If the field moves the electricity, then this shouldn't work. Another example is, if I hold the glass part of the neon bulb and the field is present, the neon light bulb should light up, but it doesn't. Also, if the field is really present, then it should not matter whether I touch or hold the neon bulb. If I have it in a proximity to the outlets, it should also light up. Remember, this is not static electricity or high voltage or high frequency. If we know anything about high voltage and high frequency, we know that that can excite the energy and the neon light bulb will light up. In this case, the manufacturer states this bulb is 65 volt AC or 95 volt DC. And to fully light it, it requires 0.5 milliamps, or for some of the more advanced, 500 microamps. And in the video, when I show it, I'm not claiming it's fully lit. That's not the point. It's just the fact that it is lit, and it raises the question, why is it lit? If it's a field that carries the electricity, then why is it lit when I connect to the actual outlet socket or the jack? Because if it was a field, it should light up in that field. Anyways, this is where the high to low potential plays its part. And I believe in magnetic energy as well as electrical energy, it's the high to low potential that makes the difference and makes the effect. It's something that's required. We'll get into this as I'm going. I'm just kind of not trying to be exactly off the slide. If the flow or current can't flow, then the field will not manifest. If this manifestation is needed to carry said energy, and I'm referring to the field is an effect or an observation, not the primary method for energy movement. If we stop the flow, we stop the energy, and we stop the field's high to low potential. This must exist or nothing would happen. So What I'm saying is you have to have some kind of gradient, a high potential to a low potential. It could be, let's say, 100 volts to 50 volts, or 10,000 volts to, let's just say, 5,000 volts. You have to have a potential there to cause this effect. And once there's this effect, you are creating some kind of amperage. That kind of amperage is generating the magnetic field. And as we go on with this journey, you're going to definitely probably have a much better understanding of where I'm going with this. All right, so this is what the electromagnetic wave looks like. So the y-axis, the red arrow that's pointing up, that is the electromagnetic field. In this case, it's a sinusoidal field going from 0 to positive to 0 to negative. And the Z, or the blue arrow that is more on the horizontal, is basically going from right to left, right to left, for example. And this exhibits how the electrical field and the magnetic field, aka the E field and the B field, how they're directly related. But I believe it's the E field that ultimately is the contributor that starts the effects, as we would call it. And then the B field enforces that. And where I'm going with that is, in earlier days, we used to use spark gap transmitters, and that was done through high voltage. And that voltage, of course, made a magnetic field. And so I believe the field is in the B field. I believe that's a secondary effect. But there is a place where that comes in, and that's more under high frequency and other things. But we'll get to that. I'm just kind of giving you something to get a feel for. So I'm going to play this neon light bulb experiment to put what I'm saying in context, that when I hold the light bulb on one lead, I stick the other lead in, the light bulb lights, and that lights because of the high low.
As you can see, I'm holding this light bulb. Here, I'll put it on the white background. So you can see I'm holding the light bulb with one hand. The other side I'm going to bring in to here, and if you get really close, you can see the neon light bulb light up just ever so lightly. See it? Right there. I'm going to do the same thing with the lights off, so it's much easier to see. And here we go. See? So when I touch the outlet, that neon light bulb is lighting, which means that there's current flowing from a high potential to a low potential. I'm a lower potential, but if the field was here and I were to hold said light bulb by the glass body, it should light up, in which it does not. And that is my point. The field is manifested by the amperage moving through the neon light bulb. And so here we go again. So you can see I'm hanging on to it, and I'm sticking said light bulb in there. And if I get as close as I can get, there's nothing. And if I get a little bit lower, you're thinking it's a surface area thing, nothing happens.
Okay, why is that not pop? There you go. Okay, so here's just to kind of validate what I'm saying. So this is a data sheet from the vendor, and it's kind of weird. My highlight isn't showing, but the A1A or NE-2 is the neon light bulb I'm using in that experiment. So it takes 0.5 milliamps to fully light, 65 volts AC, and 95 volts DC. Obviously, that's an AC outlet. Nobody's going to scrutinize that. So we know there's 120 volt power there. We know it's 60 hertz. So we know it's not static electricity. We also know it's not high frequency. We also obviously know it's not high voltage. So we can pretty much rule that equation that it's a field. In this case, there's no field that we can really say discernibly that's present. So that's why I put this video in here, is because I want you to think about what I'm getting at. And what I'm trying to portray is, ultimately, we want to understand what the Bendini system is and how it works. Well, it works by potential differences. And sometimes it's a B field where I throw a stone into a lake, or I skip a stone, I should say, on a lake. It makes these ripples. Well, this lake is a big volume of energy just sitting there doing nothing. And I take this little stone and I cast it. This little stone makes these ripples, which is energy. So if I can cast enough energy briefly, I can create this void or this vacuum, kind of where people talk about this vacuum energy. And so if I time these things right, you can obviously consume or bring in a magnetic field from another source, which we call it near field coupling, is the most common one. Another set of terms would be, we can use propagation in this case, or ducting. And all they are is ways that a magnetic field is moving through our space and time, whether it be the ionosphere, deep space, or relative space like on Earth. So I just want to put this into context, that this really isn't saying that there's a field here. And I want to make that apparent, that the high to low potential and the current flow is really where the field would manifest itself from. So I just want to throw that out there. So here we are, going back into my slides. So E field is a static or stationary electric charge, such as a proton or an electron. It can be created by time-varying magnetic fields. Any object with an electric charge generates an electric field in space surrounding it, exerting force on the other charge. In basic terms, what that really means is, if we have a generator is spinning, and it's exerting a magnetic force, which is exerting an electrical force, and those things can push on each other and create different effects. In this case, electric field. And if it's a big enough field, much like a lightning strike hitting the ground, it energizes an area or a space. So that's kind of what we're referring to here. Hopefully my chair isn't squeaky too bad on you guys. The atom and their charge levels. Okay, in this case, we're talking about electrons. What is an atom's charge level? Well, it depends on the material and how the atoms are in said material. And so what I mean by that is, like, what is the atomic weight or complex or elements involved in, let's say, steel, aluminum. And then let's compare that against insulators and such that are not deemed conductors, such as glass and porcelain. But if you get into the electrostatics, like high voltage and things, glass and porcelain will conduct electricity really, really well on a glass surface, as in actually like the surface, like your skin, which we kind of commonly call a skin effect. If it travels in a conductor, we commonly call that a core effect. But anyways, electron flow. Yes, the electrons move, and there's a big debate on the internet right now. I'd love to drop some names, but unfortunately they couldn't get back to me in time to use their names and give a shout out to them. But there's a lot of controversy on electrons moving. Yes, they do. They just do it really slow. So in layman's terms, what they do is they hand off their charge either by bumping into other atoms or other electrons, or they bunch up, and that's what creates the movement or motion effect. They don't really move that fast when they do move, so don't think they're just running down the line like water through a hose. A good analogy is, think of people moving a bucket of water. They kind of hand the water off like one pail at a time, or they dump one pail into another pail, and they move it down the line to the destination. From a side profile, it looks like it's actually moving, but the people are actually stationary, but the buckets are either being handed to each other or they're dumping the water in and they're going down the line. So hope that kind of gives a little bit of understanding of this stuff. And this all matters to have this basic foundation, because otherwise you don't really know the difference, other than the obvious: E is electric and B is magnetic. Okay, so this high to low potential that I keep talking about, like it says here, does it create flow? I certainly believe it does. But there's two conditions here, because it's kind of a trick question. When voltage is present, we get a flow. Flow is the combination of voltage and amperage or current being combined together. And just so you know, if you don't know, amperage and current are effectively the same thing. They're just the way we express it based on the way we're expressing it. Work only happens from a high to low potential. Work only happens if there is a load. Think a light bulb lighting. So you can have hundreds of thousands of volts, or you could have, let's say, 50 volts. If there is no way for that energy to go from a high to a low potential, work is not being done. Just like if I'm a person and I'm leaning up against something. If I'm leaning against something, it doesn't mean I'm doing work. Now, if I lean up against something and I move it, now it means I'm doing work. So some things to keep in mind, and the similarities between life and electronics, there are some similarities if people express it the right way. So ESD, or electric static discharge. This is a perfect example of high to low potential. This high to low potential causes a voltage, which ultimately causes a current or amperage to flow, which in turn damages the components. So, for example, if I'm a silicon wafer and I get enough charge, I could blow a hole through that silicon wafer. No different than if I took a garden hose and, let's say, I just barely cracked the valve on it. So now I'm getting a kind of a high pressure stream. And if I pointed that at a dirt wall, for example, I could push right through that dirt wall and that'd be a hole. Well, typically when electrostatic discharge happens, that's really what it does to the electronics inside. It actually blows a hole in it, or blows the little wire up that comes off the lead if it's a microchip going into the substrate or the die. But that's probably getting a little carried away. So the combination or combined voltage and current and amperage is observed or measured. This is the product of flow. And how we could observe it, for example, back to ESD, is we could X-ray it and we could see a hole in it. We could X-ray and we could see some kind of char mark in it. Obviously, measure is simple. We're just talking voltmeters, high voltage probes, electroscopes, things of that magnitude. So it is an observable feature at certain levels, and it is definitely measurable. Atoms or electrons, cancel or neutral. And this is another mucky topic for a lot of people. Yes, this is the charge balancing itself out, or the charge being removed. This is called the neutralizing effect. So what I mean by that is, if I take a proton and the electron and they were to be bumped together, pushed together, plus and minus are going to make zero. Much like if we talk about nucleuses and why they're called nucleuses, because they're generally considered neutral, and what have you. And so this is where you can actually have, let's say, too many positives, ions in, let's say, steel, and not enough electrons. And let's just say stainless steel, for example. So stainless steel is a conductor, yes, but it's a poor conductor. Why? Because it has more positive charge in the physical raw materials. So it doesn't have a lot of free space for electrons to move or pass that energy back and forth. Another thing is, think of a battery being discharged or dead. The reason it's being discharged or dead is because it doesn't have any charge, meaning the electrons really have no room to move. They're neutralized. So this there again, some general thought process here. Okay, conductors. Well, what are they? They're a medium that allows electrons to hand off their charges to one another efficiently. And that's probably the most accurate definition of it, because the better the conductor, the more power or amperage that we can move through this. And so like precious metals such as gold, platinum, copper, brass, aluminum, that's why you typically see them in electricity and electronics, is because they are very good, very efficient conductors. And, a conductor doesn't necessarily have to always be considered good because it's big. or good because it's got high strand count. A lot of the times a good conductor just simply comes down to its physical atomic makeup inside it. Okay, the atoms in the metals tell you the quality of the conductor, which goes back to what I was saying about gold, platinum, and copper. They have a lot of extra electrons in them. They have a lot of less impurities in them. And those impurities, they're again making a better conductor along with the atomic side of it as well. The atom structure will also tell you the efficiency of the conductor, generally speaking. Okay, so now we get into conductor size, small or large. And I was just talking about that. You know, everybody thinks, oh, big conductor, oh yeah, that's the best way to do it because it can move all this energy. Well, we can, but it also can get carried away where we have too big of a wire when we don't need it. But anyway, so small or large, do those atoms accelerate? Well, a small conductor will actually generate or create friction if the flow is too high or too much potential push. So what I mean by potential push or the flow is too high is simple. If I try to put 10 amps through, let's say, a 22 gauge wire, it's either going to heat up or it's just going to melt. So that's what I mean by flow and potential or push. If I'm too aggressive, even though that wire is a good conductor by all intents and purposes, it's not a good conductor because what I am trying to make the conductor do, it's not sized proper. So that's kind of what I mean. This friction is observed or measured in ohms of the increase in resistance as is the opposition of flow or opposing the flow. What that means is if I put too much push, too much flow, or have too much volume behind what I'm trying to move to this wire is going to heat up. When it heats up, it's going to cause more resistance. Resistance is going to impede the movement of this electricity and energy. And that impeding is what we're talking about here. And it ultimately could cause a catastrophic failure. The large conductor also creates a flow slowing effect. And so what we mean by that flow slowing effect is we got a big volume because we have a big space. Think of like a big garden hose, for example, or a fire hose maybe would even be better. They got a volume of water there. So it doesn't have to really go fast to effectively move the volume. So if we had a smaller hose, you'd have to pressurize it a lot to make it deliver the same amount of energy that a bigger hose could. So that's what I'm talking about here. And then I'm going to talk about a lot of this fluid stuff in relationship to the electricity electronics. So just bear that in mind because I think it's easier for some people to comprehend and get the gist of it. Okay, so the conductor has more volume or potential, which is what I was talking about. Although this volume has a slowing effect, but it also can have more push potential. And so what I mean by that is it's just a simple mass scenario. So if I took a body of water and ran it down a hose, the hose is going to determine a few things. One, at the rate that that water is going to go away from that reservoir, but it's also going to determine the amount of force that it can exert on something. And that, of course, is always based on nozzle size. Well, our nozzle, for lack of better words, is our conductor size. So, you know, can atoms accelerate? Absolutely they can. And when I refer to atoms, I'm generally speaking electrons because we're talking electricity. So just keep that in mind. Okay, so acceleration. Accelerate generates friction. If the flow is restricted too much, the flow will generate heat. AKA wire resistor gets hot when you push too much power in it, or if you have too low of a resistor, you're not opposing enough energy, eventually it'll just self-destruct and, as I call it, let the magic smoke out. So that's a friction of the electrons or the effect of the electrons trying to move through this object. So just think of, you know, taking a garden hose and you're trying to cut it off with your hand, you know, like just pinching it off or kinking it off. That's this effect the same thing as a resistor. Okay. This acceleration causes friction and increases the resistance in the conductor. For example, think of an electric toaster or blowing a fuse. Electric toaster these wires inside get orange, sometimes white hot, and that's what heats up. Well, that heat is that resistance. That's that you stopping or opposing the flow, which basically means the energy is going in, there's not much room to move, it's creating friction from acceleration, and that's generating heat. And the worst case is it's going to blow the wire apart or blow a fuse. If we create a high-low potential and then release this into a good conductor, we definitely get acceleration. And if you were to watch some of these videos out there, when they talk about electricity and fluids, they'll often talk about taking some water, pouring it in one side, and you'll watch it run across, hit the wall, bounce back. You'll kind of see this wave move back and forth in this tank. This is what we're talking about when we take a good conductor and we restrict it, and all of a sudden we open it up like full throttle. We let all that water out. We let all that energy out. If it hits a resistive part, some of that will actually bounce back. And that turbulence also causes resistance along with the physical device. And that's commonly kind of referred to as inrush currents, and why inrush currents can blow things, even though the device is technically rated for it. And that's because that push at that momentary instant is so aggressive that it actually overloads the device. So if we release this potential, like I said, into a poor conductor, the flow is restricted. And then this conductor heats, which obviously, as I've talked about, which can be observed effect known as resistance. And like I said, so I'm just kind of reiterating what I'm saying in these paragraphs. And then, like I said, letting the magic smoke out, which we obviously don't want to do because we're trying to conserve as much power, be as efficient as we can with things. So, like I said, if you guys got questions, certainly hit me up at the towards the end of this, because it'll probably be easier as well. So the path of least resistance, flow, conductor size, ohms. Flow wants the largest conductor because it's the most efficient route to the load, aka doing work. Because the conductor makes it easier for the flow to move, it also makes the high-low potential deliver more volume or push more efficiently. So remember when I was talking about this inrush current, or this inrush in general, if you took this volume that was stored somewhere and all of a sudden you let it into a big conductor and it did run into something, like I said, it could potentially destroy it. So that's, once again, path of least resistance is an expression of an efficient conductor with a volume of energy, aka flow or current or amps. And so understanding those words, I think, helps with understanding this. So current and amperage. Current or amperage is an effect or observation of flow. The more the flow, the lower the resistance has to be. Because if current goes up, resistance should go down. Doesn't mean it will. There are certain circumstances, just like I've seen areas where current can go up and resistance can go up. But generally speaking, one goes one way, one goes the other way. So if the friction or drag or resistance is less, the more the flow can happen. So if the resistance goes down, the amperage can go up. And when we mean the flow or push and the volume through the conductor. So like I said, there's the volume that is the driving force from the high to low potential. The flow is your amperage in basic sense. And then the push is the diameter of your conductor. So if you have a large volume with a large flow, you can get a large push. And that's basically because there's no resistance, there's no restriction. It also determines, if you're talking a stationary object, like I roll a marble down a ramp, it also would determine how long and how far it can go. Same thing with water, obviously. If I open the hose, it's going to shoot a set distance until that volume starts to deplete, and then it's going to slowly turn to a dribble. So it will also say how far it will reach out in a liquid sense, as well as how far it will reach out in a physical sense. So power is the expression of watts. Watts comes from current, resistance, voltage, generally speaking. Ohm's law is really the telltale for that statement. And expression of watts or power there again, it's the same thing. It's just how we use it in what context. For example, we all measure our houses in kilowatts. So that's 1,000 watt hours. That's how we're doing that. Nobody says I have 1,000 power hours. That just doesn't sound right. So we just say it's 1,000 watt hours. So then maybe that helps you, in the basic sense, get that meaning, I guess. This is the basic example of flow. Flow happens because the volume with push from a high to low potential doing the work into a load. And like I said, if it's not doing anything, it's potential. Similar to high voltage, similar to static charge. It's just sitting there. But it initially needs to have some reason to go from this high potential to a lower potential. Once that reaction occurs, this is when this all comes into effect. And when I mean this, I'm referring to, we get current, we have resistance, we have voltage, we have flow, we have volume, and we have push. That's when all these parts come into motion, when they all actually start to do something. Okay, so E-field closing thoughts. There again, this is just a general example. It's not exactly correct, but for the general audience, it's probably mostly correct. So I got a power plant. Think of these examples this way. We have a power plant with a generator that is making power. We need to move that energy or power to the load, aka a house, to do work, lighting a light bulb. We make a very big high to low potential using a generator. So the generator isn't like selling you electrons or things like that. It's just making a volume and a pressure, if you will. Then this volume gets the push. And when I mean it gets the push is the volume builds and builds and builds, and it's stored there. We push it down the line because we need to power a home, for example. So the volume comes from the generator at the power plant. An example is a 50 megawatts of power. So that's a quantity of volume and measurement that is this power plant is capable of producing. It doesn't mean that it's only got 50 megawatts of power. It means it continuously generates 50 megawatts of power. And then that would theoretically be distributed through the power lines and eventually divided across all the homes. This volume with the push gives us the effect of flow, current, or amps. The path of least resistance is simple. It's a good conductor. The wire that the energy or power is transferred with, meaning the overhead power lines that you see every day that you drive by. The path of least resistance is a big conductor. And there again, I reiterate this. Wait, no. The conductor only needs to be able to handle the volume and the flow to the house. Meaning, we don't need to put a 14-foot diameter wire up on a wood pole because we don't need that. We're using high voltage, low amperage. It's still all stuff that will definitely kill you. It still really cooks a hot dog pretty cool if you have a pole transformer like I do. But anyways, so you only need that conductor, like I said earlier, to be as big as the power demand. So although, yes, you could put a big conductor up there, it's just not physically ideal. The reason for this is to control the flow. And it is. We want to control the flow because that way if something gets unbalanced, the wire will kind of take the brunt of this a bit and absorb some of this. And it will actually smooth the power grid out. It's actually pretty cool to watch. I wish there was a video I had for it because it's an interesting thing to watch what these substations can do to regulate the inrush and the grid loads. But anyways, the flow and push and volume, and then the resistance. And of course, in this case, the resistance is the wire or the conductor over the distance. So we have two factors here. We have the material of the wire, let's say aluminum versus copper. If it's aluminum, it's usually twice the size of copper. And that's for two reasons. One is the current capacity. The other is for the strength differences. And the other is also obvious weight. So if you get into semantics of things, if you measure out aluminum and copper, you'll find out to move the same volume of electricity, they're relatively equal. That's kind of a fun, useless fact, but that's kind of how it works out. Okay, so the reason for this control, like I said, is to control the flow, the push, and the volume so that we just don't overload things. For example, if we use a large efficient conductor, we could send too much volume and too much push into a house, and we're going to blow fuses and appliances. This would happen because the work would be overloaded, from high to low potential difference. So meaning that if there was this effortless big pipe, the power plant wouldn't see the house or houses as a load. It would just try to push all of that power down the line. And that's because everything is always trying to balance itself, like an equilibrium, kind of like yin to yang, black to white. They're always trying to balance. And so that's where that statement kind of comes from. And it'd be nice if somebody would actually make an official video at some point in context to prove this. But it does make sense because we can do these basic experiments and prove that scenario. Anyways, so meaning if we have too much volume, flow, or push in a good conductor, there again, we'll now let out the magic smoke. And so that's kind of the general overview of E-field. I know this is really pretty rudimentary and pretty basic, but I think it portrays what the E-field is in layman's terms. I realize that I have an engineering degree. Steve has an engineering degree. I also realize there's 5 people with PhDs and all that. But the problem is, if you're coming into a conversation because you're curious, if somebody doesn't explain the basic constructs, you really aren't learning anything, and it's probably just frustrating you and discouraging people. So that's kind of why I'm doing this. It's more to give people an overview. And you want to get technical, we can get technical at the convention after hours and social hours and things like that. Okay, so I'm bringing back up this electromagnetic wave slide again. And there again, B field through observation, no math. So there again, the electrical field is the Y, the red arrow pointing up. The magnetic field, B field, is the blue arrow kind of pointing to my my left, lower left. And so they are directly proportional. They both do need to be here. There are some scenarios where the electrical part can kind of be perceived as being stripped away. And I'll go into that before I go to the next slide. And so I'm sure we've all had this. We've been listening to a radio station. We drop down into a valley and we lose the station we're listening to. And there's the 2-part thing here, and I'm not going to get too technical with it, but there's the wave portion where the wave is not going into the valley. And then there's also the field portion that would manifest on the antenna, which would be kind of like a siphon where electrons would come into the antenna in relationship to the field. And then that would be converted into, let's say, an audio message, like music, for example. So there is a few other factors here. The other thing where this happens too is if you're in the mountains typically and you buy a lot of really heavy iron, the magnetic field, because it's magnetic, will get attracted to iron and it will also absorb that signal. So that's why you can also get some of that signal lost when you're in the mountains. So just kind of, there again, trying to put this in context. Hopefully that makes a little bit of sense too. So I'm putting these web searches up here because we're getting ready to go into this B field experiment. And I think you guys will find this relatively fascinating. So I'm just going to read a little bit of this. I'm not going to read all of it, but you probably should ask this question because you're going to see this next video is really going to present something that you're probably not expecting to see. So anyways, so here we are. Can you stick 2, yeah, I know I spelled 2 wrong, North Pole magnets together? It says no, you cannot stick, or you cannot naturally stick 2 North Pole magnets together. Okay, like poles repel. I'm not going to read the rest of the slide. There is a bunch of these slides, and I'm trying to prove my point here, and I'll get to it once I'm done with this before I start this video. Can you stick a North Pole magnet together using electromagnets? It says yes. You can stick magnets together using electromagnets, but the method depends on whether you are trying to attract 2 separate magnets or combine their fields. Okay, there again, if I have an electromagnet, it's just like a permanent magnet. If like poles attract, same poles repel. So just there again, you can ask these questions if you want in Google, or in my case Brave, to validate this, because I do want to make a point that you need to understand this, because if I'm a kid and I'm trying to figure out electricity and electronics, this is really not helping me at all, because this is conveying the fact that you can't do certain things. And I'm going to show you, oh yeah, yes, you can. Okay, so here's another slide. Can you stick a North Pole magnet together? Generally, no, you cannot stick two North Pole magnets together, because they're, again, like poles repel, opposite poles attract. One more slide here. Can you stick a North Pole together using electromagnets? Yes, you can stick North Pole magnets together using electromagnets, but they will violently repel each other until the overcoming force to make them meet. So once you push them together, they'll fly apart. So the reason I'm showing you these slides is obviously one is through Brave and one is through Google. It wants you to see the misconception or the confusion that's being portrayed here. And then this video will really be, quite honestly, be pretty impressive. Okay, so we got a couple more of these. This is, can you stick the North Pole magnets together? Generally, no, you cannot stick two North Pole magnets together. So there you go. I just want to be unbiased where I got Brave and I've got Google. Because you got to remember, Google's got, millions of people looking this stuff up or potentially looking this up. So the last question I've got here, or statement I should say, can you stick North Pole magnets together with an electromagnet? They go, yes, they will, but they won't stay together on their own. So what they're saying is I can forcibly put them together, but they won't stay. All right. So I got to do a little house cleaning here. I apologize, guys. So, all right. So here we go. I'm going to start this magnetic like poles video. Neo, a C6 ceramic magnet. Got some, pull force there between the magnets. So I'm going to throw this one more time up here just so you can see it, because I think it's neat. So we got this really strong magnet. Let's pull. What are we dealing with? North Pole, North Pole. So these two North Poles, first of all, are stuck together. And then we've got this North Pole with this South Pole are stuck together. And we've got the South Pole and the South Pole that are stuck together. So right now we have that North Pole and the South Pole and the North Pole. And there's a coil in between it. And I have to get up to nearly 4 amps to finally get enough power to repel this. Okay, so what I'm demonstrating in there is, once again, a high to low potential. And so you see that I have this really big, strong N52 grade neodymium magnet. And then, as you've seen with my magnetic meter, that little red and green beeper, basically, I was showing you that both poles were the same type, and she stuck right together. And at first glance, you'd go, well, that's impossible, but it's not, because of this high to low potential. So back to my Google slides and my Brave slides, and this is what I'm getting at about, I wouldn't say misinformation, but maybe it's just not helping you. If you're looking up a subject and you want to learn these things, well, why doesn't somebody say, hey, if the magnet is stronger, the two poles of the same type could stick together, as I just willfully proved in that video that it can be done. But everything I showed in those slides said it couldn't be done. So this is the other reason why I like to kind of, I wouldn't say dumb it down, but I like to be in more common terms, because this is a lot more palatable. I just showed you without a shadow of a doubt that I have a meter that can tell me north and south poles. I just demonstrated that north pole locked to that north pole on that electromagnet. The other thing you noticed is the only magnet that left in the experiment was the ceramic magnet. And that's because the permanent magnet and the electromagnet still were not strong enough for it to separate. So the electric magnet was still being influenced by the permanent magnet. And when those two magnets started to increase their strength, because I was increasing that voltage, aka the current, aka the wattage, aka the flow, aka the volume, that's when that ceramic magnet kicked away, because it was the weakest link. That would be the similar effect of like a resistor. In this case, if you want to call it a resistor, the magnet threw itself away because it couldn't take the magnetic energy. It couldn't confide to it, or couldn't magnetize itself to be additive. So they repelled each other, just like that electrical energy when it goes into a resistor or a bad conductor. It's actually fighting, it's bucking its head. So that's where the B field and E field are very, very similar. You just got to have somebody presented in that right context. Sorry, so I'm going to get into this, and it's going to be a lot of the same thing. So the B field is a magnetic version of the E field, as I just got done talking about. Yes, but only using magnetic strength to create a current or flow. The reason for this statement is the E field needs to be present to make a B field first. However, that's not the case if we're talking magnets, as in permanent magnets. Remember, Tesla's first used a spark gap to make a radio transmitter. That E field, high to low potential, aka high voltage, created the B field, and said radio message was transmitted via the B field. And so this is where the E field influenced the B field. The B field then was the messenger, aka just like that radio station was sending that down the line. And when that radio tower on the other end, or antenna, I should say, would be more appropriate, was in the right length and the right field, it decoded that information, as we know, as music or somebody talking, such as myself. Okay, so the Lenzing law. This is the resistance or drag of the B field. So this is exactly the same thing as a resistor in the electrical world. So the resistance or drag of the B field. Resistance, drag, or eddy currents are the B field's opposing forces or the opposite reaction. So we always talk about in physics, there's a reaction and then there's an equal and opposite reaction. Same thing is applied here. Same thing with the E field. If we have one field or one electrical charge that's higher than the other, it can actually push one charge a different direction. Same thing with a bigger magnet can push a smaller magnet. And I'm sure we've all seen these videos 100 times. Somebody puts a magnet on their table and there's another magnet on the bottom and they're moving it around and you can see the magnet move. Yeah, okay, so that's basically what we're talking about. This is the fundamental principle, stating that the direction of the induced electromotive force, EMF, and resulting current away opposes the change in magnetic flux. So in layman's terms, if we have, let's say, like copper or aluminum, and we take a magnet and we either slide it down it or we put it in a pipe, like a copper pipe, the magnet is going to move really slow. And that's because the B field is trying to make an E field, or more importantly, I would say the B field is trying to interact with the E field. In this case, the E field is sitting there doing nothing, but because the magnet is trying to push its potential on the E field to make the E field do something. And so then the E field makes a field again, which counteracts the magnet. And so that gets this slowing effect. So we would call this, electromotive force, because that's exactly what it is. It's the opposing force that manifests because of this B field interacting with the E field. And then the E field is interacting with the B field. So hope that kind of makes that a little bit easier to understand. Okay. Why does a magnet slow down with certain materials? As I kind of talked about this, these eddy currents are opposing flow, but only in the magnetic form, meaning eddy currents only exist in the B field or magnetic energy. The B field is interacting with the E field or trying to, as I said earlier. The B field is the effect or observation of the E field's presence. As the magnet falls through the copper pipe, the B field is making a current or flow that tries to make an E field. This is where the confusion starts, because we're trying to figure out who's first and who has the influence. Because we are using a permanent magnet, its potential is really large, which it is because it's a permanent magnet. It has way more density per ounce, per gram, per surface area, any of that. So its density is incredible. It has a higher potential and will influence the copper's conductor because, aka, it's a lower potential. The copper has only a certain amount of materials in it, but you have to move these materials faster to get this reaction. This is where that slowing down effect comes from. So as a magnet is trying to be pulled down by gravitational forces, it's influencing a greater force, which is what makes that E field, which makes the B field, which also is that slowing effect. This high to low potential is what creates the flow in the first place. So the high to low potential is probably the big takeaway out of this. You have to have the high to low first. It doesn't matter if we're talking E field necessarily or B field. I believe it's E field that has to do this first. But in permanent magnets, it's the other way around. And that's why I say this is why it's confusing. So remember the neon light bulb experiment. This directly conflicts with this, and it does. So if I hold the neon light bulb, I'm a area, my body is acting like a conductor. It is also acting like resistance. I stick it into said conductor, which is bringing this high potential, in this case, 120 volts. So it is higher than I am. So therefore, it is flowing through the neon light bulb and into me. And because I have a little bit of, E field or electron energy that's releasing off of me, this flow kind of continuously will happen. And it will also happen because the 120 volt AC is always going to be higher than me. So this is why I say these things and why I believe it this way. So in layman's terms, this is called the chicken and the egg scenario. It's where it depends on your context of where we are looking at this. If you're talking electromagnetics, it starts in my world from the E field. If you're starting from permanent magnets, it's already in the B field because the magnet already has the energy density. Okay, so this is just a slide talking about the field lines, and you'll see there'll be a magnetic field strength that's got a little yellow circle there. So the stronger the field, the closer the field lines are to the magnet. And as the magnetic signal decays, the layer lines or flux lines get farther and farther apart. And so we look at the Earth, for example, because we know the Earth has a magnetic field. Well, at the center of the Earth or near the center of the Earth, we have this really strong field, just like what this picture portrays. And obviously, as we get farther away, the field lines also don't bend as much. And so one could argue that gravitational waves, if you look at it from a planet construct, because we're getting closer to space, we're getting farther away from gravity, so gravity doesn't have as much pull. And so we could argue that's what bends some of these field lines, and that's a total different conversation, total different debate, but I just kind of want to throw it out there. And this next slide here is just to get the E field and B field construct a little bit better. So we could say if we put a positive current in on, which should be your guys' screen, the right side, and we put a negative, and we receive the negative on the left-hand side, the south side would attract the flux lines or the magnetic signal. So it'd be kind of like a deficiency, if you will. And then the north side, it would be pushing it away or accelerating it. And it's also easy to look at it this way, because if you ever want to know how a coil needs to be polarized to make it an opposing magnetic field, like in the Bendini, for example, this gives you the construct of how the field has to be set up to make that repulsion. And there's also different Bendini systems they have where they're also in attraction mode. And all that comes down to is the way they flip the two coils in the basic schoolgirl version. Well, there again, we won't get quite so much into that, but we will point out some other things that I think are definitely valid, or things you want to see or want to know. So here we kind of do, and I think Steve calls it what's electronic gang signs. This is what we call the right-hand rule. It's a simple rule to determine which way the magnetic field is going to manifest and the polarity of the said manifested magnetic field. And it's also in relationship to the polarity of the current moving through said coil. And there again, the only reason I brought it up here is, you know, how do we know which way the Bendini is if it's all north and the motor is running? Well, if our North Pole magnets on our wheel are all north poles facing out, you can look at the coil at the bottom of the Bendini system when you talk about a single coil unit, and you can put your thumb up just like this picture does. You know, like you can see my thumb right here. You're like, hey, the Fonzie, right? And that tells you where the North Pole is. So now you know why the magnets repel. They go away because they're two like poles. So it's just another way to tie E field, B field into the Bendini system a little bit. And they're again on a more entry level, elementary level, but it's still, once again, a thing that if you don't know, you don't know. And since I don't know what audience I got, well, it's hard to say. But I'm trying to cover everybody as best I can with this basic presentation. Okay, so magnetic strength. What is strength? Well, magnetic strength is measured a few different ways. Tesla, Gauss, flux density, or N grade or N rating. And all that really means is the energy density of the magnet. So what does it mean? This means the pull force or permeability of said magnet, and that is general terms. The density or flux or Gauss, those are more scientific terms to really mean the same thing, but we're not trying to get overly technical here. Like I said, no math. So we're just trying to keep it simple. This permeability is the material, the materials that went into making or charging said magnet. And so why I say making or charging is so sometimes we have something called a rare earth magnet where Earth makes this for us from thousands of years of hot, cold, compression, yada, yada. And then there's others that are actually electrically made. Neodymium magnets are predominantly electrically made. Ceramic magnets can be electrically made, but a lot of times they also come from Earth. So just kind of understand that. We can charge it using electricity, which is kind of interesting because didn't we just say that the field is what carries the energy earlier on? But yet we're saying we're using electricity, which emphasizes what I said and demonstrated with that magnetic or with that neon light bulb. So just there again, why I'm trying to point these out, because people may not get this. So the magnetic material are the physical materials used in making the magnet, such as iron, nickel, cobalt, and neodymium, as I said earlier. The stronger the magnet, the higher to low potential the magnet could have. And the reason I say could have is because, of course, a magnet is only as strong as the materials as well as the materials it's interacting with. For example, really strong magnet will interact with stainless steel. You heard me say that. It will interact with stainless steel. Now, if you have steel, obviously that really strong magnet, you probably will never get it off. But this is what I'm getting at. So there are certain materials where the magnets will do different things. So just bear that in mind as well. So depending on the type of materials in the magnet can also interact with how it interacts with, let's say, stainless steel, for example, versus aluminum. Okay. For example, a strong neodymium magnet could have up to 1,000-pound pull force. So what does that mean, first of all? Well, from the magnet's perspective to an object, it means it has the equivalency of pulling, and we're generally talking deadlift. So we're talking, if my lower hand here is the metal on a table, and this top hand right here is the magnet being pulled out. So it means that if that piece of metal that was on the table was 1,000 pounds, it means it could actually lift that. So that's what the 1,000 pounds of pull force could mean, for example. In this case, like I said, a piece of iron from a few feet away or through an object. So you could get some really big magnets, and you could obviously put them through a table, like I talked about earlier, where you have one magnet on the bottom, one magnet on top, and you can manipulate them, and they follow each other, kind of like this kind of a motion, for example. The other thing too is, through an object is a concept too, because wood, obviously, we can push the signal through. Metal, depending on certain scenarios, we can also push that signal through. Even though the magnet wants to stick to the metal, if the magnet on one side that's doing the moving will likely influence the lesser magnet on the other side. So there again, this high to low potential. This is why I cannot reiterate this high to low potential issue and its real importance. Okay, so magnetic direction. This is the way the magnet is charged or polarized in a pull direction. So what I mean is it axially? So if I take a pencil here, right here, is it magnetized where this is the south pole and this is the north? Or is it diametrically, which means splitting it right down the middle? The top half would be north, the bottom half would be south. And then axially is also what I was referring to earlier. This is an axle, and this would be here or here. So there's three general different types of how magnets are done. They're done on a surface. If you're talking like a square or rectangle, one side's north, one side's south. If you got like a ring magnet that kind of looks like this little plastic piece here, hopefully you can see it. The inside could be south, the outside could be north. Axially would be, this could be north, this could be south. And then diaxially would be through the middle, going up could be a pull, through the middle going down could be a pull. So hopefully that gives you an understanding of the direction. Hopefully you can see that too. I realize it's black, so it might be hard to see. I'll have a little bit better visual show and tells when I'm at the convention. Just like I said, just to give you an idea. All right, so magnetic strengths and effects. And this there again is dealing with this high to low potential. If one magnet is stronger than the other, it is possible to stick the same poles together. Yes, it is. We demonstrated that in the video. In my case, it was an electromagnet because I don't have a weaker neodymium magnet to go to a larger neodymium magnet. Otherwise, it actually would probably do the same. Because if it did it in the electrical world, I don't know why I would not do it in the magnetic world, because they're directly related. So if it's good for the goose, it should be good for the gander. So if somebody does that experiment for some reason and it doesn't work, I would love to see your notes on it. I would love to see the flux density. I'd love to see the surface area. So if anybody does do that and they want to put me on blast and hate me, give me your facts, give me your evidence, do a video. I would love to see it. It's one thing I haven't been able to do. I've got just tons of things going on, much like Steve. Anyways, so magnetic strength and effects. Basically it comes down to there again, that high to low potential difference. And that's really the moral of the story here, because the E field is the same deal. High to low causes a current flow, which also creates work. That flow has volume behind it. Well, the magnets still have the same thing. A really dense magnet's got a really good volume because it's really densely packed. So even though it's not physically really, really big necessarily, the energy that's inside it is where the volume is. And there again, the flow and the push is that magnetic energy, the B field reaching out, interacting with the other object or other magnet. Okay, so there's another thing too that probably people misunderstand. In magnetic surface area, or magnetic surface, yeah, magnetic surface R, magnetic surface area, nice. Can a wider surface area of a magnet control or manipulate The other magnet, yeah, we just talked about that. That's that high to low potential. So it's practically impossible to get a magnet to be the same size and have one be stronger than the other, first of all. So let's just make sure you understand that. Not saying it can't be done, because the guys in China are working hard. I'm sure they are. But typically, magnets of the same size, and I mean literally and figuratively, meaning it's 1 inch by 1 inch, 1 inch. The next magnet's 1 inch by 1 inch, 1 inch. Unless you're changing the type, meaning ceramic versus neodymium, their densities are virtually the same. So that's why I say if you get a smaller neodymium and a larger neodymium, they should stick together north to north, because the larger one should be influencing it. Like I said, I haven't been able to do that, so don't quote me on it, but it should work. So yes, once again, the high to low potential difference. That's the deal, the high to low potential difference. This effect is caused by the flux density or the strength of the magnet, also sometimes called surface exposure or surface area exposure. And so think of surface area like a conductor size. The bigger the conductor, the more the flow, the more the current, the more the amps, the more the volume can move through it. Magnets are no different. They're the same exact thing. Big magnet can stick to big things or pull big things. Bottom line. So some closing thoughts here before I go into the Bendini stuff, assuming Steve is okay with me running on here. Can current flow move in both directions? I have some beliefs that it can. I'm kind of hoping to bring that to the presentation at Tesla Fest coming up here. I will see if I have that experiment ready. So we really don't know. Is there something called magnetic current? There again, I believe there is, because I believe not only do magnets have their own field, I do believe they have their own current. And I believe that if you could put magnets side by side and with the right, let's say, flick, kind of like a domino, if you will, that I believe you could move that magnetic energy from one magnet to another and eventually push the field out farther on the other side. There again, it's an experiment I've been waiting years to do. Once again, life gets in my way, so I can't do these things, but it is a thought that I have. Okay, so here again is the end of the E field, B field presentation. And now we're going to get more into the Bendini side. I assume Steve hasn't cut me off, so we must be good to go. We're looking at about an hour and 15 minutes here. So here's my contacts again, just for some people that might be joining late. So if you're interested in the Bendini kits and some of the other future gadgets that are coming up, southwestgadget.com is your go-to. If you want to email me and talk to me, Gmail, social.media.info.us@gmail.com. I will be putting videos as I see them fit out on social media, info.us on YouTube. I will have the comments disabled because I have had problems with YouTube monetary or removing my monetary, as well as kind of blacklisting me, not promoting me, blah, blah, blah. We've all heard that story. So the comments on the video won't be there. The contact information is Gmail. There is a live phone number that is an actual functioning phone. You could call it. It is upstairs. It would ring. Just get it dumped to voicemail. Tell me your name, your number, and what you want to talk about, and I will do my absolute best to get in contact with you. But I do work full time. I do have 2 children, and I'm trying to invent or reinvent the Bendini system and make some improvements to it and sell those for people to learn. So I'm a busy guy. So that's all I got to say about that. So here is the references for the artwork in both of these presentations. Should the copyright Nazis care, if you were to click on those links, they would take you right to the graphic files or the web page and where I got those graphic files. Okay, so now we're going to get into the John Bendini Energizer, and that's what he calls it. And I think that's probably an appropriate word because it energizes a field, and it's debatable what field or if it's multiple fields. So we're going to get into this. All right, the Bendini system video. Unfortunately, will be reserved for the conference. So Bendini demonstration will only be shown at the conference. And why I say that is I'm going to have a hands-on exclusively. I'm going to show and tell. I'm going to also talk about how to measure the energy going in and out of the system. I will provide some equipment under my watchful eye. You can use my equipment, or if you'd like to bring some stuff yourself, under my guidance, of course, I will show you where to put things and make sure you don't hurt yourself or my machine. They're, again, one-on-one questions too. I mean, I love to talk about this stuff because, hey, I live in a basement. I'm a nerd. That's what I do. And so I'm super excited to be here because for once in a long time, I get to talk, and I love talking, especially about cool stuff. So, like I said, don't miss out. I mean, seriously, help Steve, support the channel, support me, support everybody involved, and go to the convention. I realize it's a lot of money. I'm really honored that Steve is helping me out on that. I really am. I'm also really honored that I'm here because I've been sitting on this stuff for years and years and years. So anyways, like I said, big shout out to Steve. Thanks, man. Love this opportunity. Hope this is doing good for everybody. Hope this is doing good for Tesla Tech. Like I said, love to see you guys. All right. I love the thumbs up. Sweet. All right. Let's get on to it. Okay. So I'm going to do this little video coming up here. Well, I shouldn't say little. It's about 7 minutes. But it's a beautiful video because this is where young amateurs and even some college guys get tripped up. So I'm just going to read this slide here, and then I'm going to jump right into the video because we're getting tight on time. So sample time video. Hold on, Steve. Don't do that yet. One of the many reasons we fail with the Bendini system. This is a big one. Not necessarily sample time always, but we have instruments that we believe are reading something, but we don't know how to validate if they're reading things right. Okay, so next line here is, what is sample time anyways? What does it really mean? And I will explain this in layman's terms, and we'll get some slides and some videos to collaborate this. So sample time is we look at something over a period of time. Sample time is exactly what it sounds like. It's how many times do we look at that over a period of time. So I'm not going to go any further than that. I'll explain a little further down. Do we know when the equipment is reading incorrectly? Well, that really depends on your experience and your education, because I have a beautiful oscilloscope that we're going to demonstrate in here. Love the thing. Not a lot of money. Great instrument. But when I got it, I did not realize that low frequency stuff was going to be a problem for it to sample. And so I thought, hey, this would be a great video to bring to Tesla Tech. It'd be a great video to bring here because a lot of people probably don't realize that their equipment's lying to them. Or if they did think maybe it's lying to them, they don't necessarily know how to make sense out of it. So this is also an awareness. How can our equipment lead us astray? Does the equipment really see the data correctly? Well, if you don't know how to program the machine right, why would it, right? Well, the same argument. If the math wasn't right in it because somebody thought it worked this way and it worked a different way, well, that could be a problem too, which is why I bring a lot of these slides and why I'm doing this presentation, because there's a lot of basic things that people think are one thing, really are a different thing. So that's kind of where I'm going with this. Can the equipment actually display the data correct? Well, there again, that depends on even if it has a way for you to set what you're wanting it to look at. Is the math actually done right in the first place? And, are you using it properly? That's probably the biggest one. So, this is basically what some of the ways that we can be misled using different equipment. So that's what this is about. So I'm just using an oscilloscope here in this case. I think the video will, sum itself up. And so we're going to talk about the sample rates here. And like I said, so if we look from 0 through 13, that horizontal line T, that's time. And then if we look at the blue lines with the blue dots, the vertical lines, that's our sample rate. So I'm just going to give an analogy here that will probably portray this And I'm going to show you another picture and another basic analogy, and then we'll get into the video here. So, for example, if I'm only sampling, let's say, one sample. So if I go 0, 1, the 3 dots, and then I, for example. Let's say I'm only sampling what would be the 3 dots. Okay, I'm seeing a really high number there. Now, if I take the same data and I sample from 0, 1, the 3 dots, and I now have to do a couple of things. One is I can see that I now have a waveform, first of all. But two, if I'm looking for voltage, I need to average those together. So I'd add 0, 1, the 3 dots, and I's values together, and then divide, in this case, by the samples. So I'd divide by 4 because I have 0, 1, the 3 dots, and I. So if we don't have a machine that can read samples fast enough, clearly we can see how we would get, messed up numbers, incomplete information. So this is why sample time is a big thing. And if we're talking Bendini stuff, we're talking radiant energy, we're talking high voltage spikes, we're talking, fractions of a nanosecond, just boom, just really quick bursts of power. Well, if you aren't having this happen fast enough, your oscilloscope straight up may never see it. It'll be really obvious here on this next slide when I do the same experiment. So amplitude, like I said, would be your voltage in this case. Time is going left to right, or the horizontal. Amplitude is going up and down. So for example, if I take the first dotted line, the second dotted line, obviously I can see a high to low there. If I take the first dotted line, the second dotted line, the third dotted line, and the fourth dotted line, I now can see that there's a valley. And the valley is that little dip. However, if my sampling only is sampling on that dip, I'm not seeing the rest of the extra energy there because I'm only seeing that dip. Same argument that if I'm using the first dotted line and let's say the fifth dotted line, I'm seeing a higher voltage. I'm assuming that the dip is not a dip. I'm assuming it's filled in. But if that sample isn't happening, I can't see that. So this is where the oscilloscope stuff comes into play, because we want to be able to see that there isn't this dip or this rise. Because if we can't see it, we can't quantifiably say it was there. We also can't say that, oh, this is the voltage from point A to point B, because we're not able to view it. So that's what I'm getting at. And this is, why things kind of matter about understanding things. So here again, here's the system explained. So in the slide that I'm getting ready to, or video I should say, that I'm getting ready to do here, this is the system and how it's set up. The power supply is on the top left, is supplying power to the Bendini system. The Bendini system is sitting on the table in the center. The 48 volt DC 40 watt light bulb is just to the right of the Bendini system. The oscilloscope is a Siglent SDS 1202X-E. It is in the top right. It is the instrument with the wave patterns on it. We give the Bendini system electricity from the power supply, and it transforms the electricity into high voltage spikes. These high voltage spikes are what normally would go into a charge battery in conventional Bendini theory. Conventional Bendini theory is the output of the Bendini system pushes negative electricity into the positive post of the battery. So we're actually putting a negative energy into a positive terminal, just to make sure that was stated. In this case, it goes to my recovery board. So on this system, I have a special board that harnesses the radiant energy, the negative energy the Bendini system makes, converts it into a positive form, and then is transferred into the battery. The recovery board converts this high voltage spikes into positive voltage and current or amperage. This energy is what is making the light bulb flash. AKA more on this later. Okay, so like I said, here's the still picture. So you can see the power supply is on the left, the black and red with the green lights. The Bendini system is obviously front and center on the table. The light is just right of that. And then the oscilloscope, which we are going to go into now with this video, is right up on the top with the waveform. It's got a bunch of green lights on it. So I am going to start this video, and oops, why is that not showing me? Are you guys able to see that? I'm not showing that up on my screen at the moment. We have it. Oh, there we go. There we go. That's better.
Looking at the time division up here on the top. And then we're looking at the wave right here. And what we're going to do is we're going to try to measure from the peak to the valley of that wave. And then obviously the space in between is the off time. And the purpose of this is to show why things sometimes have to be done through observation, and why you have to know about these things, because if you don't know, you're going to see things that you think are something when they're actually not. And first of all, I'm going to hit the run stop button, which you can't see on the oscilloscope, but the wave is going to stop moving. Okay, so the reason for this is, first of all, the space here and here is 1 second per division. Like I said, you can see that right up here, hopefully. Then you can see the RMS voltage, which is supposed to be from this peak to this valley in that square wave. And then of course this is the off time, and then the pulse itself is the on time. So what I'm pointing out here is when I change the time divisions, meaning this will start scrolling again, and I'm going to change the time division. So all I'm changing is this number right here. And the time division, just for if you don't understand, is left to right, and the voltage per division is top, or from bottom to top, or this middle here up. And here we're on 50 volts per division. The frequency, if somebody cared, is there. The sample rate is right there. And this is kind of my point. The sample rate is only as good as the samples taken over a given time. So I'm going to start this. So what do I mean by that? Well, I mean how many times it can see this pulse or this series of pulses. So if you see right here, this number is fluctuating. All I'm going to do now is I'm going to change this time period, and you'll see it because it'll put up a number up on the screen, so you can see how I'm changing this. So I'm just going to stop at 1 millisecond, and you're going to see a number that is vastly higher. And so what I'm going to do is I'm going to hit the run stop button once again, and it might take me a couple of times to get this right, but here we go. So as you can see, we have a much higher number. I'll do it one more time. We have a much higher number. Now I'm going to go back to the 1 second per division, and as you can see, this number is vastly lower. Now how I get past that, and the point of this video is this: I'm going to hit the run stop again. All I'm going to do is I'm going to move the trigger, so the trigger is going to start right down here and go up. And so this is how I figure out voltage on an oscilloscope when I think there's a time constant problem. So here is what I'm going to do is I'm going to put this up here. You see that little white line? Doesn't stay up there very long, but you see that little white line. Okay, so now I'm going to turn this up to basically right about here, and we have 42 volts. Then I'm going to go turn it up some more, go right in the middle. I'd say 59, maybe 60 volts, right? Okay, so if we average this number out, we just basically take the two numbers, add them together, and divide them by the samples. And that gets our average. Well, that's average is kind of how the measured square, or RMS, is calculated. So right here, we already can tell that there's a major discrepancy in that math. And that's the math that I'm talking about, where you can't always trust your instruments, and you have to be made aware that your instruments can only see certain things. The moral of the story is this oscilloscope is not a multi-billion-dollar oscilloscope. And I'm over-exaggerating, of course, but the point is this is designed to see higher frequencies, not lower frequencies. So when you try to look at something like a pulse of energy, you need to be made aware that your sample rate has to be fast enough in order to see it. Otherwise, if you're looking for the RMS pulse, in this case voltage, you're not going to get that accurately. So I'm just going to reiterate that again. We're at 21.4, and all I'm going to do is change the time divisions, and obviously you can see the number changed again. Now obviously it's going to change dramatically once I take the run stop off, as you see. And if I just simply go down to 1 second, once again you see how it misrepresents the value. And anyways, that's what I wanted to show to you, and to give you something else to look at a little later. I'll show you the setup of what I'm doing, probably just a still frame. But so this is my point, is math can be a double-edged sword, especially on instruments. So if you're not made aware of these things, it can really trip you up. And in the Bendini world, which is where this context is coming from, this is probably the number one thing why people couldn't figure things out. But that's for another video here coming up. Okay, we're ready to go back to slides. Okay, so this is where I'm gonna just play another video here, and basically what I'm doing is I'm flashing this light bulb from the energy being collected off the Bendini system, which is running into my recovery board. And that's what's actually generating this oscilloscope shot that I use for this sample timing. So I have a 48 volt light bulb, 40 watts. So you may or may not see the power supply in the back corner. I don't really care if you do or don't. It really is not the point. The point is I'm taking what normally would be high voltage spikes that you once couldn't do anything with other than maybe charge a battery, and I'm converting it into positive energy that you could use to pulse charge batteries. So for example, if you had a solar system, for example, you could take this Bendini system and take a small solar panel to run the Bendini system, and then this thing would be running in the background. The recovery board then would be taking the lower voltage up the smaller solar panel and allowing you to charge a 48 volt battery bank. So let's say you had a 12 volt solar panel or 18 volt solar panel, you could now do something to a 48 volt battery bank. So it's just an example, but I want to use a flashing light bulb for one other reason. And that reason is I was doing this experiment with my recovery board, and I thought I had it on a 1 second time constant. And it was when I hooked this light bulb up that I realized my math was incorrect. And you would think an RC time constant formula should be pretty easy to calculate and figure out. Well, so did I. But I learned once again that it's sometimes nice to have a visual representation or an observation. And obviously I have this beautiful oscilloscope. Don't get me wrong. But the moral is, if you didn't have an oscilloscope, this is a way that you might be able to get yourself closer to knowing that you're at least in 1 time second. And for example, you could just say 1/1000, for example. And if that light is predominantly running or being lit up for that 1/1000th, you probably have 1 second. So I'm going to
jump here to this video and get this out of the way. So this bulb flashing, let's see if it'll be cooperative. Hopefully it will this time. Okay. So like I said, it's just a simple video, but if you look at the bulb and you look at the wave up on top of the oscilloscope, you'll see that they are actually, that pulse is coming on the screen the same time that bulb is lighting. I'm going to play this one more time just so you see that. So like I said, right in the very beginning, when that first pulse comes in, here comes the second one, boom. So I'm using this as a visual indication that, first of all, the wave is being properly represented. Because there again, we're dealing with two possible problems. One is we're not sampling enough, or there's some kind of delay in the math because maybe it's oversampling and it's causing it to process data slow. So by having an incandescent light bulb gives me a good solid way to validate what my oscilloscope is doing into relationship to what my light bulb is. And just another fun fact, this light bulb normally wouldn't be here. This would normally go to a battery, in this case, a 48-volt battery. And the reason I show this light bulb is because if you have the battery connected, you barely see any waveform here. And that's because the battery is, let's say, at 40 volts or 38 volts. Well, you're only going to see the difference on the oscilloscope. So I chose the light bulb as a definitive way so you could see the full signal. And then if anybody wanted to look at the time constant and go, yeah, that's 1 second. Yep, not going to argue that. That's why I did it. So that's what that's about. All right, so back to the slides here. All right, so I think I got like 5 or 6 more slides and then we'll call it a day. So here we are. I apologize if this is getting long for people. I got to be up early in the morning, but hey, I'm struggling through it. I gotta say these things, and I hope this really is helping you guys. I hope this is shedding some better light on something. Because I tell you what, when in the beginning days, I was so frustrated because I have an engineering degree in the background in this, and I would ask questions, and it was either being too literal for people or too technical for people, and it was just, oh my God, it was just a struggle. But anyways, the Bendini system, or the Bendini board system explained. So the Bendini system is basically a mechanical oscillator. Why do we call it a mechanical oscillator? Because it spins magnets. We have a bicycle wheel with magnets on the outer side of the wheel. These magnets are arranged so that the North Pole faces outward or aligned outward. When a magnet gets near, it will induce a voltage in the trigger coil or inductor. And I guess I'll explain an inductor and a coil. They're the same thing. The coil is commonly referred to as a coil because it's hundreds of wraps typically. An inductor usually is only a handful of wraps. Effectively, they are one and the same thing for the novice viewer out here or listener. So a coil and inductor, generally think of them as being the same. There are differences, but for the layman's terms, they're the same. This induces a voltage, this induced voltage, will turn on the NPN transistor. This transistor will induce another coil called the power coil or inductor. In a Bendini system, the schoolgirl system specifically, there are 2 coils, commonly called a power coil and a trigger coil. The trigger, what starts the event, the power coil is what makes the magnet move, as well as the energy being harvested. Or the disturbance in the vacuum, the disturbance in the space, the B field around the device converging into the B field in the coil, or the E field being pulled out from stray electrons being influenced in the coil, or I should say coils. So this transistor turning on will induce another coil called the power coil or the inductor, as I said. So there's 2 coils, so just keep that in mind. They're 2 separate turns of wire. So the trigger has got a start and a finish, and the power has got a start and a finish. So they are 2 separate coils in the circuit around the same bobbin, which is what the coil is wrapped on. And then there's a ferrous material, or as John used, welding rods. And the reason I use welding rods is it was a very good quality steel that would hold a magnetic charge just a little bit, really wouldn't necessarily be magnetic, but would also cause a magnet to be attracted to it. So there is a design reason that he did this. But anyways, I just figured I'd throw that little extra tidbit in there. This power coil directly connects to the battery, or excuse me, this power coil directly connects the battery to the coil or the inductor, generating a much larger field. And what I mean much larger field is, once again, the power goes into the coil, the electrons are moving and getting excited. That excitation and that movement, that flow, that current, that volume of energy creates the B field. So that electrical expression is E field and then makes the B field. The B field is ultimately what is going to push the magnet away. So when this energy conducts in the transistor, it will create, or it will induce a charge in the coil or inductor's E field and create a magnetic field B field. That will push the magnet away, which is what I just got done saying. So we make an E field makes a B field pushes the magnet away. In this process of said field being created, it creates a high to low potential with voltage and magnetic energy. They both happen at the same time. So we push a voltage in, then we stop. During that push, we also are now making our magnetic B field. When that magnetic B field stops because the E field stops, the B field now induces an E field, which inadvertently makes a B field. The induced E field goes to your charge battery. The B field is used to push the magnet along. Hopefully that's not too much of a mouthful or a tongue twister. When the magnet is pushed away, the collapsing fields, both E and B, will generate a high voltage with very little current or amperage. This is what I was talking about. E field makes a B field collapses because the E field collapses. That spike or high voltage is put away to the charge battery because it has very little amperage. It's just pure high voltage. So that's what I'm talking about. This is what I mean by that. This voltage can be hundreds of volts and is directed at the charge battery. I have had horrible luck with this. I have seen amazing things. I've seen batteries come back that have been sulfated using the Bendini system in this negative charge fashion. I have seen some battery types that will take the negative charge fashion and charge and not be degraded. And I have seen other batteries that I have straight up killed. So mileage may vary. These this high voltage spike that is our generator are generally called radiant energy. John Bendini himself calls it radiant energy. I think Tom Bearden calls it radiant energy, energy from the ether, E field, B field. There's all kinds of verbiage for radiant energy. They can even say cosmic rays. I think Tesla uses that expression, cosmic rays, as radiant energy. This radiant energy is now being redirected into the battery. Remember, this radiant energy is of a negative charge level. So the only reason I stress this is because there's people that are DIYers, there's people at home, there's people that are going to possibly get influenced by this video. I want to stress to you, do this at your own accord. I am not responsible. Tesla Tech is not responsible. This is information only. This is not a guarantee. You take that risk, you take that assumption. And that is your responsibility, not Steve, not Tesla Tech, not Ryan Thompson. Okay. As long as the magnet keeps moving by the coils, this process will repeat, and it will. It'll repeat indefinitely. With each passing magnet, the cycle repeats unless you load the wheel down. What do I mean by load? I mean by drag. Let's say you put a fan on it, like Bendini did. He always put a fan to say, hey, look, it's moving air at the same time it's charging batteries. Really cool. I like that. You also could put a pulley on it and run it to something. And there again, you're loading it down. Eventually, if you load it down too much, the wheel will slow down and stop. So to make the Bendini system initially work or start, you must push it momentarily with your hand or spin it. You got to give it that little bit of energy from you to make it do something. So another thing to note in this slide, in the other video that I just showed with the flashing light bulb, the primary battery is supposed to discharge slower than the batteries we are charging. Note, I'm using a power supply. I am only using a power supply for a demonstration purpose. In real life, this would technically be running off of a battery. So just want you to be full aware of that Bendini system has an input battery and charge battery. Okay, so this is actually the schematic drawing that I made for the Bendini board that is actually on my Bendini system, which these boards and the schematic information is common domain. So you can screenshot this, you can steal it, you can do whatever. It's probably a much nicer translation than what's out in the open wild. So I don't have any problem with you guys using it. Don't worry about it. I wanted to make sure you also see this. I have cited the patent here because this is not my work. I am just a presenter. I'm just trying to rekindle the flame and maybe demystify and maybe get people relearning about, I wouldn't say it's a dead technology because it's definitely not a dead technology, but I would just say that it's something that I think we need to spend more time on. And I think we're finally at this point with the community, me making a kit that's got this whole unit all built together if you want it, or if you just want to buy the boards. I'm happy to support all that stuff. I'm not trying to sell anything in the video here, but I'm just saying that I'm happy to stand behind it. So if you guys have questions, you blow it up, you need it fixed, I can do all that stuff. Obviously, I don't do it for free, and I do it on my own leisure, but just throwing that out. So this might be easier for most of you guys because it's just easier to follow. So this is a terminal block here where there's different inputs and outputs, right? The dark black traces are the top layer. The gray traces in the background are the back layers. So here's a neon light bulb, and I'm going to talk about this because this is a critical thing. I don't know if John really addressed this exactly. This sole purpose of this neon bulb, mind you, is the same neon bulb that I used in the video with me holding that neon bulb, putting it on that 120 volt outlet. This is designed to keep the voltage lower than the collector emitter junction on this transistor. In this case, it's an NPN. This lights up under two conditions. One, you don't have the battery connected. Two, you are trying to over voltage this transistor. Okay, that is what the purpose of this neon light bulb is. This lamp that's right here, there again, I don't know if he talks about it. This is a current limiting device. We have this resistor here. We have this variable resistor here. This is a visual indicator that you are pushing the circuit too hard, meaning this light should be lit a little bit. There should be a little bit of light coming from it. Might even pulse, but it should not be lit bright. It should not be lit constant. This is the same reason that I used that light bulb in that video that I flashed. It was an indicator that I was running for 1 second. Is indicator to show that I was getting voltage increase in that oscilloscope shot. This is an indicator to indicate that the circuit is functioning. And if it's pulsing or flashing, indicates that it is triggering. So a lot of people don't understand that. I will give this little tidbit about this. This is a variable resistor here. If you buy the boards from me, they have a set of numbers on them, and it makes it really easy to discuss over the phone. Hey, go to this number. What does your wheel do? Does it speed up, slow down? Do you get more charge, less charge? So I have a graduated variable resistor here to make it easy for supporting these things, because my idea is to make sure you understand this and then you can actually do something. It isn't just to sell you something like so many people have done 1,000 times over. Same thing with the Bendini forums, the Yahoo groups over Unity, all that stuff. I loved it. It was great. I interacted with a bunch of it, but mostly it made me frustrated because nobody made a standard. Some people were making a Bendini system using a skateboard wheel or an inline skate wheel. Some people were using a bike wheel. Some people had 3D printers. Some people used a wood rotor. Some people machined aluminum. Well, if you're not going to follow exactly what John's doing, you're not going to get the exact same results. And I think that was one of the biggest problems with all of the Bendini work. He took the world and captivized them and got everybody engaged, and everybody was like, this is so cool. But it all fell apart because they didn't have standards. I offer those standards. I don't say they're cheap, but I have a 3D printed frame. I have bearings. I have circuit boards, and obviously I'm giving you a presentation. So I kind of like to think I know something about this. Like I said, and this is all just my interpretation from learning and what have you. So I hope this, like I said, is not too boring for the Ivy League people. Hope this isn't too bad for the everyday people. I'm trying to get this broad audience. I'm trying to wake the world back up again. All right. So the recovery board explained. The recovery board takes the high voltage negative spikes from the Bendini system, converts the high voltage with no amps to current, and switches this energy to positive energy. So I'm taking this negative radiant energy and I'm converting it by putting it into a storage device. And then that storage device allows me to convert the polarity of the energy back to conventional electricity, like what we have in everyday environments. The recovery board is triggered by a voltage set point. This voltage set point in this case is set to 48 volts. If you're wondering, yes, we can change this voltage set point. You have a 96 volt battery bank you want to charge? I'll change one part, boom, it's 96 volt compliant. You want it to be 24 volts, boom, it's 24 volts. You just change one component and that changes it. Once the 48 volts is present, it triggers a MOSFET. So basically, it gets to a voltage and then turns on an electrical switch. So think of a switch like your light switch in your house. You turn it on and off, right? So this 48 volt preset is what turns on this MOSFET, aka this switch. So it's like me going, oh, we got enough bucket in the water, flip, I'm going to flip that switch. In this case, it's a MOSFET. So the MOSFET is also turned on for a duration of 1 second. So remember that oscilloscope shot I showed you. That is proof that is 1 second. That flashing light bulb is proof it's 1 second. The time constant on the oscilloscope is proof it's 1 second. And if you get a stopwatch out, you can look at the scope wave or the flash rate and also validate it's 1 second. So here's all the different ways I'm quantifying this information to ensure it is exactly what it's supposed to be. Then the system turns off after that 1 second. This will repeat as long as two things are present. One, the 48 volts is met and the load is connected. If there's no incoming voltage spikes, the recovery board remains off, meaning it does nothing. It's not doing work. It's just sitting there. Also means the light won't flash, aka the 48 volt light bulb. Second, if the light or load is not connected, there will be no high to low potential, and the system will not switch, meaning it has to see the presence of a load. And I will tell you this particular revision does have a known bug that if you blindly ignore this thing, you will kill it. And then you'll have to send it to me, and then I'll have to fix it and charge you for that and the freight. So just make sure, like John always said, make sure you hook your charge batteries up first. And Jeff, if you're listening, my buddy, you can tell these guys at the presentation that you didn't do that. Sorry, Jeff, I just had to throw that out there. So Jeff, if you're wondering, is the guy that's behind Southwest Gadget. He is the sales guy for my kind of me and his partnership, I guess. So he's the guy you're going to talk to on the phone when you want to buy one of these cool things. So make sure to shoot out to Southwest Gadget. All right, so enough with the self-promotion. So anyways, so there'll be no high-low potential. So therefore, the system won't switch. This also means the recovery board will not switch either, which obvious because there's no work, there's no load. Why would it? Okay, so that's the basics. So now what? Okay, so now this is where we get maybe into a little bit more technical stuff, some general disclaimers about some things. Okay, so what's the difference anyways? Well, here's where things really change. First off, we're using electrolytic capacitors to store the charge temporarily instead of batteries, making the volume flow and push. The battery really doesn't like the negative high voltage entering from the positive battery terminal. After all, the power or voltage is reversed. I mean, I wouldn't like somebody pushing me backwards for any length of time, let alone upstairs. So why would the battery not like to get, power the same way? Battery wants to get power through the positive and through the negative, not negative through positive, positive through negative. Although this although this works and some have had success, my results, aka, my results were bad in most cases, unless I was desulfating batteries. And that's a whole nother topic, a whole nother lecture. Anyways, aka, that's why I made the recovery board. I made it because I was having a hard time, and I extensively work with batteries, big, gigantic batteries. Matter of fact, the big garbage can batteries that Bendini had in some of his earlier videos, those big monster 2-volt cells that are out of the phone companies. I work with big batteries like that on a day-to-day basis, and so I do understand batteries. And where I'm going with this is I had far more damage done to batteries using the negative energy. And since I've converted to my recovery board system, it has been vastly less. There are places when the negative energy is super helpful, though. But there again, that's a totally different conversation. So why am I doing this? Well, if we step up the voltage using the Bendini system, we need a safe way to step the power down. I mean, if it goes up, it's got to come down, right? Well, we also want to make it come down as efficiently as possible. If we just released all the stored energy from the electrical capacitor at once, the battery could explode or boil off water. Because why? We have too much volume, really good conductor, we have too much flow, and we have too much push. So we're being too aggressive. We're putting the power in the battery too fast. And that's why we have batteries that have amp hour capacities. That is a determined amount of energy that the battery is allowed to release or absorb. And if you technically push too hard, either going in or going out, the battery will boil off water. Water goes away. The battery chemistry changes, eventually leads into sulfation, could also lead into hydrogen gas, could lead into explosions. Lithium batteries, please, 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 please make sure you have a battery management system. Do not just take lithium batteries and hook high voltage to them. It is not a good time. I have not had experiences, but I have seen colleagues that have. So do not start with lithium batteries. Please remain to lead acid batteries or nickel cadmium or nickel metal. They're proven stable batteries, and even though they're not as dense watt-wise, they are safer for this experimenting, especially if you're new. Okay, these are some of the basic examples. This would happen because of the volume flow or push leaving the capacitor with no restriction or resistance, which is what I just got done saying. There's a lot of stored potential in the capacitor. Anybody will tell you this. If you're new to this, please look up the subject matter of capacitors because you do want to know about it. If you guys give me a shout out, I can maybe do a video or talk about that a little bit. But like I said, please look in the capacitors to see you're a little bit more aware of them. What would we would have too much high to low potential in energy. So meaning we would obviously there's too much push, there's too much volume, there's too much flow. We're just being too aggressive. So that's the problem. So because the Bendini system makes high voltage, negative spikes, and radiant energy spikes, they are hard to see or view with certainty, which because the time is so minuscule and so fast, it's hard to capture it. This is why we typically measure the effect or gain at the charge battery. So this is why we try to quantify the energy that we put in the battery. But if you don't know the time period and the time constant, or I should say, how often we're putting said energy in, we don't have any way of really telling if we're doing anything at all. Since the Bendini system makes or extracts radiant energy or energy from the vacuum, batteries or any other electrical device do not run on this type of power. They do not run on negative electricity. They do not run on negative resistance. They do not run on radiant energy. Or power from the ether. They don't. This is also the problem. So this is why the Bendini system can't just power your home, for example, or endlessly charge your batteries necessarily, and then your batteries are in your home. Radiant energy is really nothing more than E field and B field energy. Generally speaking, that's what it is. It's E and B field. There are some other factors, but E and B field are the main takeaway, along with high to low potential. For example, free electrons in free space can be attracted either by the E field or the B field, or a combination. So if I had high voltage next to the Bendini system, then that electrons spilling off could actually go into the circuit, and because there's a flow, could be additive. The B field is if there is, let's say, a high voltage discharge into a coil, that near field coupling from one coil to the other coil could also be an additive factor. So this is why I say E or B or a combination. With the attraction, we can see or observe the extra power, which we can, depending on how we're measuring it, of course, and with what instruments. The extra power can be measured by batteries becoming charged. Most anybody on their first Bendini build, if they get the Bendini system to spin, will likely see a battery charge right out of the gate. And they'll go, oh, wow, this is cool, which is great. But then you got to learn about batteries and chemistry and how this works. And again, that's another video. That's another discussion. All right. So I am just about done here, and I apologize for this crazy length. We then either convert it with the recovery board to positive conventional power, or we put this energy into a battery. And that's basically what we do. We use the recovery board to convert it to positive energy to charge a battery. And so here is my contact information once again. I do apologize if you guys are going, oh my God, this guy just never shuts up. Yeah, that's what I do. It's my thing. But I try to convey as much information to you as I can, because there's a lot of this stuff that I don't believe is out there, or if it is, it's just buried so deep. So there is my contact information. Thank you guys very, very much for listening to me talk about this and demonstrate this. I hope to meet everybody at the convention. It should be an absolute blast. There again, thank you, Steve. I cannot thank you enough for the opportunity. See you at Tesla Tech.
Thank you. I learned a lot, and we really don't have any time for questions right now. We're way over. Anyway,
yep.
We'll see. I'll see you all next week. We'll probably do an open floor next week because it's Mother's Day. And you all have a great week. Bye.
Okay. Just on a side note, if anybody does have questions, feel free to bounce them to Steve or myself at our social contacts here. And then we also can maybe do another video sometime as well for, live in person kind of deal.
Okay. Anyway, we'll see you at the conference, and I want to remind everyone we're at 30% now, so you should get your registration in. The hotel's taking reservations. So y'all have a great day.
All right. Thanks again, guys. See you at the convention.